Welcome to a lesson with Dr. Powell. Let's take a look at what a planar graph is and how we can think about Euler's characteristic equation or formula for such graphs. So, what do we got? A planar graph is connected, and that provides a nice connection between the incidence matrix range and the number of vertices. The number of vertices in the incidence matrix of a graph is the number of rows. Now, if it's connected, after you do Smith normal form, there's only going to be one row of zeros. And the range of this matrix, the range of the Smith normal form, particularly the dimension of the range, plus the dimension of the kernel, is going to be equal to the number of columns. The number of columns is equal to the edges, and the dimension of the range will simply be the number of vertices minus 1. Now, how can we have a nice depiction of what the dimension of the kernel is? So, when we're computing Smith normal form, in particular, realize that we eliminate cycles. In fact, if you have any cycle at all, the incidence matrix will send it to 0. In fact, it's safe to say that even the dimension or the kernel of the incidence matrix is made up of combinations of cycles, and its dimension is just equal to maybe some standard basic cycles that you can add together and take multiples of, and so forth. So if we had a graph such that we could lay out all of the cycles flat in a nice way, so we can kind of think about the cycles flat, then we'd actually kind of see the basic cycles. We could actually visualize what the dimension is by what the standard basic cycles are that we can add together to get different elements of the kernel. So here in particular, I have this one. So there's 1, 2, and 3. So the dimension would be 3 in this particular case. Now, often and when we have a graph that we can lay out flat, we might imagine that we can lay it flat not on the plane, but on a ball. Now, if you had a ball, then you'd have this and this and this, and we can call these faces of the ball. We also have a face that's outside, a fourth face. So the kernel, in that case, the dimension of the kernel would actually be equal to the number of faces minus 1. So you could say faces minus 1, especially if you were to flatten these out and kind of arrange it or kind of extend these into a shape that had 4 different faces, perhaps. So we have face minus 1, v minus 1. This is the condition, or this is a condition that we use when we think about a graph that's planar, where we actually get the dimension of the kernel from just viewing these different faces right here. So a planar graph has this idea. So if we assume that a graph is planar, now by rearranging this equation right here, we end up getting v plus f minus e is equal to 2, or more commonly, v minus e plus f is equal to 2, where v is the number of vertices, e is the number of edges, and f is the number of faces. So if a graph is planar, then we have this idea holding. Notice that direction. If it's planar, then we should be able to put cycles out like this and be able to get the dimensions to correspond this way. Planar in its as a definition, as a rule, pretty much means that you can lay out a graph flat like this to look like this, and there's particular without any crossings or overlaps. Thanks for watching.